The Daytona International Speedway in Daytona Beach, Florida is famous for its races, especially the Daytona 500, held every February. Both of its courses feature four-story, 31-degree banked curves with maximum radius of 316 meters. I'm picturing kind of a non-circular shape, but a maximum radius. We could imagine a circle drawn here in this spot having a radius of 316 meters. If a car negotiates the curve too slowly, it tends to slip down the incline of the turn, whereas if it's going too fast, it may begin to slide up the incline. Part A is find the necessary centripetal acceleration on this bank curve so the car won't tend to slip or slide up the incline. And part B is calculate the speed of the race car. We're supposed to neglect friction here, and the neglecting friction means we're treating it as though the road itself were perfectly smooth, and the tires are the friction between the tires and the road are contributing nothing to the force at all. Now you can see I've drawn a diagram here, or well, the book has a diagram, and I've added some things to this diagram. Now, this is an unusual problem because my intuition says it ought to be done one way, but the authors of the text have another way. My intuition says, now this is an unusual problem because my intuition says it ought to be done one way, but the authors of the text have another way. My intuition has it done by this, the version 1 up here. Now, if this were the case, then we would have a normal force of mg cosine theta acting this way, or well, we'd have the normal component of the gravitational force pulling down on the car in that direction at mg cosine theta. And so we'd have an equal and opposite normal force pushing this way, which would also be mg cosine theta. And then this component would be mg cosine squared theta. And this component here would be mg cosine theta sine theta, because this is angle theta up here. And then we would say that this force, mg cosine theta sine theta, is equal to our force centripetal, which would also be either, depending on how we do it, mass times our centripetal, well, let me just write mass times centripetal acceleration first, which is also mass times omega squared r, or mass times v squared over r. So with that in mind, with mg cosine theta sine theta on the left-hand side, and m times the centripetal acceleration, and m times v squared over r, that gives us sufficient amount to solve for a sub c and v sub c, or I'm sorry, v tangential, because we know our radius is 316 meters. We know the m's will cancel out of all parts. And we know theta is I think they said 31 degrees. So we know g is 9.8, and so everything can be solved for from that. However, they did not get g cosine theta sine theta equals the m times the centripetal acceleration. Instead, they're going to imagine the component of the gravitational force. If this is mg, here's the normal force, and here's theta. This is mg cosine theta, and here is the component of the gravitational force in the parallel direction, mg sine theta. At the same time, they imagine the centripetal force, which is going straight that way, force centripetal, the component of the centripetal force in the parallel direction, which is also this direction, which is m times a centripetal, and then there's no force, which would be F, which would be the force, I'm sorry, it's not ma centripetal, this is ma centripetal, and this is ma, I'll have to draw a line to it because I didn't leave myself enough room, ma centripetal times the cosine of theta. And so then they set mass times a centripetal times cosine theta equals mg times sine theta. The component of the gravitational force in the parallel direction, mg sine theta, equals the component of the centripetal force in the parallel direction, ma centripetal times cosine theta. So when they do that and they work that out, they cancel out this, and they get a centripetal equals g sine theta over cosine theta, or tangent theta, which would lead, which also, if you wanted to solve that for v, you would take v squared over r equals g tangent theta. That's supposed to be an r, or v equals the square root of g r tangent theta. Now I came up with this modified version of what we have down here, with this being mg cosine squared theta, this being mg cosine theta sine theta. What if we modified this to version 3, and in this case we imagine that normal force coming up this way, the actual length of this side being mg, and our theta here, the length of this side being mg, and this being theta here, and we want the parallel force, or the force along the direction of the centripetal acceleration. I'll call that force centripetal. And then let's just write down the equations for SOH, CAH, TOA, and we'll have sine theta equals opposite. Let's see, this is our force centripetal over hypotenuse, which we don't know yet. We'll call that our normal force. Ka goes cosine theta equals cosine theta equals adjacent mg over hypotenuse, which is our normal force, and tangent will be tangent theta equals opposite, which is our normal force, over our adjacent, which is mg. So here, here, I made a mistake because opposite is force centripetal. All right, and then, so our force centripetal is mg tangent theta. And that is mass times centripetal acceleration, which is mass times v squared over r. And this can be solved by first canceling out an m. Let's see. Divide by m, cancel out an m, cancel out an m, cancel out an m. And then we'll have g tangent theta equals a centripetal, and v equals square root of rg tangent theta, which is the same answer we got from version 2. Only thing is we have suddenly changed our normal force to mg over cosine theta, which makes it the normal force actually be larger than the gravitational force, which is kind of odd. So I have to say I'm in doubt about whether the authors of this or whether this is actually the correct reading for the force of friction. I think maybe either the authors made a mistake or and you'd have to try and run a test to see what the engineers at the Daytona 500 actually said, and see if it was truly a matter of a tangent theta here, or if it's a g cosine theta sine theta.